Okay, I'm trying to make the recordings as small as possible. I think that was too small, but let's continue. So in number 3, a buffer system is set up with a concentration. We already know what a buffer is. You have an acid and its conjugate base. It's already set up with the following conditions, and your pKa is 5.5. Remember that when you already have a buffer system established, it's very easy to go with validity equations, which in this case is basically the Henderson-Hasselbalch. So you can simply say that the pH is equal to pKa plus log your base divided by your acid, okay, which is equal to 5.5 plus log the base divided by simple equation, simple arithmetic, okay? Simply cancel this one. You get log half, which is basically negative log 2, plus 5.5, and this should be 5.2. So let's go with this one. That's your answer. Good. Number 4, or questions 4 and 5, refer to the following titration curve. Before we go into it, let me explain the titration curve for a little bit. What I mean is, let me explain the different areas in a titration curve, okay? So the first thing that you need to differentiate in this case, note where the curve starts. انتبهوا وين ببلش الكيرف. Curve starts right here. You are, remember that this is your pH, this is your volume. You start here. It means you are in an acid region. In an acid region, it means that you are basically titrating an acid. What is this acid? What is the pKa of this acid? Is it monoprotic, diprotic, etc.? We don't know yet. This is where the titration curve comes in place. So I'm going to follow the curve. After the acid, I will notice that the curve will move into a simple flat area. This is the buffer region. This tells me that the acid is a weak acid. If I go even further, I will cross the first equivalence point. I will cross an equivalence point, whether it's first or second, I don't know yet. If I continue, another buffer region, another equivalence point. It means basically I have 2 equivalence points and 2 buffer regions. This means that this is a diprotic acid. It's H2A. When we know this, we can actually determine the properties of the acid. So I know this is an acidic pH. I know at the first buffer, my pH is equal to pKa, pKa1, remember that. At the second one, my pH will equal to pKa2. هدول significant regions that you have. And remember, the first one will be at your equivalence volume, it's half. The second one will be at 1.5 your equivalence volumes. And you have a very important region that you never forget, which is basically point B. Point B is what you will have at this point is only HA minus. And HA minus is governed by a pH, which is equal to half pKa1 plus pKa2. Review the validity conditions that you have, because this will explain. If you need me to explain it, let me know, but you should already know this. You should already know the validity conditions of this point and of this point and of anything in that region as well. Enough, let's go back to the question. Which one of the following does the titration curve represent? A strong acid? No. Diprotic acid? Yes, that's enough. titrated with a strong base. Of course, all titrations will happen to the strong base. Go back to the conditions of titrations that you have. What are the pKa values that can be obtained from the above titration curve? Very simple. I know the first pKa, which is pH equals pKa1, which is basically 6.3. And I know the second one, which is pH equal pKa2, which is 10.3. So it's 6.3 and 10.3. Where is that? There it is. 6.3 and 10.3. You don't need to segregate the titration curve as I did, but it's a good way to know how to formulate everything. So, number 6, determine the pH of a 0.15 aqueous solution of KF. KF is a salt. Basically, KF will dissociate. I don't know if you took solubility yet, but salts dissociate according to their KSP and according to their equilibrium. If you don't have the KSP, it means KF will completely dissociate into K plus and F minus. That's very good. I already know from studies in K plus as a spectator, it will have no effect on the pH in my medium, in my water-based medium akid. However, F minus is an unknown. I don't know it. What I do know is that they gave me the pKa, or the Ka, sorry, of HF. This tells me that HF F minus is a weak species, and F minus is the conjugate base, or the base in the couple. What will happen is that the base, which is F minus, will react with H2O. It will be a reversible process because it's weak, to give HF plus HO minus, production of HO minus. To calculate the pH, remember the validity, start with the first one, go to the final one. According to validity, I'm going to do both validity and the conventional method. The pH of this solution will equal 7 plus half pKa plus half log C, which is the concentration of your species, if this entire value is greater than pKa plus 1. Okay? So calculate it, 7 plus half pKa. You already know how to calculate pKa. Log C, you already have it. You get a value of 8.165. Is this greater or equal than pKa plus 1, which is basically 4. pKa is 3.15, so it's basically 4.15. This is valid. It means that this is your pH. Let's choose it. Which one is it? It's D. This is your pH. I suggest that you memorize the validity conditions. أكيد أول شيء understand them, do the derivation itself, and then memorize them. It's not hard to do because with practice you will be able to do it very easily, especially if you're applying for the concours and you're applying for the medical school, the pharmacy school, or the dentistry school, because you're going to need every second. If you're not applying for those schools, you can afford to actually do it the conventional way, even though I don't suggest that you do. Conventional way is basically you take your reaction, something that you learned. Here's the parroting method that they taught you, which is basically you take your reaction, you start your conditions, the ICE table, if you remember it, the initial change and equilibrium table. Okay, you get to a point when you say, okay, the initial concentration is 0.15 minus the change x. X is governed by the equilibrium and by the Ka. H2O, we already know the concentration of it, and we already did the derivation for why it's not included. X, basically your Ka is equal to x squared divided by 0.15 minus x. Find x, which is the concentration of HO minus. your X is the concentration of HO minus. And if you have the concentration of HO minus, then your pH is equal to 14 plus log HO minus.